Hello, this is Nicholas Vinen from Silicon Chip Publications, and today I'd like to do something a little bit different. In the past, I've talked about either a single specific article published in Silicon Chip magazine or a one issue of the magazine and the articles within it. But today I'd like to talk about a series of articles that we've been publishing since December 2025. There are 10 articles to do with these model railway DCC systems. So DCC stands for Digital Command Control. And this first article here explains the history a little bit. So it used to be that model railway systems basically would just apply a DC voltage across the rails in the track, and the model trains would pick up the voltage from the wheels on either side, and if you gave it a positive voltage, it would move in one direction, and a negative voltage, it would move in the other. Obviously, this makes it a little bit difficult to run multiple trains on the same set of tracks because they will get the same voltage. They may not run at the same speed. They may eventually crash into each other. Ideally, you want to be able to control different model trains at different speeds, different directions. You may also have things like lights, sound effects, displays in the model railway system that you'd like to be able to power and control separately from the trains. So DCC was a system developed to address this, and what it does is it applies a high frequency AC across the rails. That's then rectified and filtered by the trains to provide power for their motors. But the AC also contains digital signals that tell each train what to do. So the trains would have an address. You could send a packet to an address to say move forward at half speed, and one train would respond to that and start moving. So obviously you need some kind of a processor in each train to decode the data and follow the commands. And you also need some kind of a system to deliver the correct signals to the tracks. Of course, most of these things can be purchased. You can buy trains that adhere to the DCC system. You can buy base stations that drive the tracks. They tend to be fairly expensive. They're not, there are different, multiple different people making these, so they have a range of prices and capabilities. But we thought, well, why not design a system that you can build yourself? And because it's a standard and it's an open standard where the specifications are published, theoretically anybody can design on decoder, which is what you call the electronics in the train, or a base station, or any other accessory really. So that's what we've done. So the first article, well, we have published articles on DCC in the past, but in this specific series, we're starting out with a decoder. So you can see here the small board that goes inside the train that has a microcontroller, motor drive, a rectifier, and some MOSFETs and other bits and pieces. And that's everything that you need to control the model train. And it comes, well, we've developed the software to do all the decoding and so on. And if you buy a kit for this, which we have, it comes with a program chip, so you just solder it together and away you go. We've tried to keep the cost down so that these are competitive with commercial systems. In fact, it's probably cheaper, but of course you have to do some work to assemble it as well. So here's this first article on the decoder. Here we have the circuit diagram. Obviously, to keep it small, you need to minimize the number of parts. So we have a microcontroller. You pretty much need a microcontroller to do the control logic. Bridge rectifier to generate the DC from the tracks, but we also feed the AC from the tracks to the microcontroller through some resistors so it can sense the signals. We have a motor driver chip that drives the motor under control of the microcontroller, and then we have 4 MOSFETs, and they can be used for things like lights, sounds, smoke generator, that sort of thing, so that you can remotely control those. So you can send signals to the chip to control the speed and direction in which it drives the motor, and you can also send signals to switch on and off these 4 loads, whatever they may be. Normally, the first one would be lights, the front lights on the train that light up when it goes forwards, and then the second one would normally be rear lights, and by default, it will drive those automatically. So if it's going forward, it will switch this on, and if it's going in reverse, it will switch this on. But you can change that. You can control these individually if you want. The other 2 are basically uncommitted, so they can be for whatever other accessories are on the train. Here's the parts list, so that's what you get if you order the kit. And there's the decoder and some heat shrink with it. There's an optional capacitor, which is, it's a good idea to fit. And what that does is, if the tracks have, say, some corrosion or a gap or a bit of debris on them, the train is driving along and it hits that and it loses connection to the track. The capacitor will provide power for the train to keep going, get past that, and get power again. But it's not absolutely required, so it's up to you whether you fit it. And because this is the first article in the series, we'll have a glossary, and we also go into quite a bit of detail. These DCC devices, especially decoders, have a number of what are called configuration variables. They're basically values that you can set in the decoder that it remembers, and they're things like its address, the speed calibration, so on. And you can program these remotely, so you can actually set these when the train is on the tracks. But usually what you do is take the train onto a separate track that's just used for programming, and you would program it there. Anyway, there's a standard system for doing that, which we support. Here's the diagrams that show where all the components go on the board, how to assemble it, how to wire it up. Some photos showing it attached to an actual chassis. There's obviously no shell on there, but we have checked that the shell will fit. It does depend on the size of your locomotive. That's pretty much it for the first part. Now, a decoder in itself is useful, but really you need more to the system. You need a base station, you need other bits. So in the second article, January 2026, firstly we have this explanatory article that talks a bit more about how the DCC system actually works. So this is not a project, but it does refer to the decoder, and it shows our base station, which was also published in this January issue. So with the base station and the decoder, you have enough to actually drive the trains. And we talk a bit like this is a here it shows what I just described before, a separate piece of track that's used to program the trains, which our base station has support for that. So you can see there are two outputs here. One is intended to go to the main track where you're actually running trains on the layout, and the other is for a separate programming track. And that has the advantage that the programming signals won't interfere with any of the other trains. And there are certain things you can do only when you're programming this in this way, when you have just the single train on the track, because it can send data back to the base station by modulating the load on the track, and that wouldn't work if there were other loads on the track. So we talk a bit more about the base station, the messages that you might get on the screen. Probably let's look at the base station, because that's kind of required to understand that. So this is what drives the tracks. It provides power to them. Obviously power needs to come in, so it runs off a roughly 12 volts DC. There is a range. It can go a bit higher, a bit lower. And through the touch screen on here, you can control trains. You can set their speed and direction, turn lights on and off, that sort of thing. So this is responsible for both driving the tracks with current and voltage to provide power to the trains, and also encoding all the signals that are needed to control them. Here's the circuit diagram. It's based on a Raspberry Pi Pico 2 microcontroller, GTN8962, basically motor drivers to provide the track voltage, and they can deliver several amps, so you can run several different trains. Then there's a smaller motor driver here that drives the programming tracks, because obviously you're only sending signals and there's only one device. There's a switch mode power supply here, so that the incoming voltage, which can be between 8 and 22 volts, is efficiently converted to 5 volts to run the microcontroller and the screen and that sort of thing. Otherwise there will be too much heat to deal with. So it's a relatively straightforward circuit. Oh, and we also have this 8P8C Ethernet style connector here, and that can be used to connect extra controllers, so you don't have to use the touch screen, and you can even have multiple people controlling multiple trains simultaneously. We'll get into that shortly. So here's the base station assembly from the back. You can see there's the main board here with the screen in front. There's the main board. It's relatively straightforward. There are a fair few components there, but a lot of the complexity is hidden in the Raspberry Pi, which comes pre-assembled. You can see the motor drivers here. There's the parts list. Again, we have a kit. In fact, I think we have a kit for everything in this whole DCC series, so you can put together your own DCC system just from our kits. Here's the diagram showing you which parts to go where. Some screenshots showing the settings screens, the control screen, programming screen, details on how to prepare a box to put this in, a bit of information on the Arduino software. So we're using Arduino to program the Pico. We provide the source code for that. People can modify it if they want. So having now looked at this base station, which is the other key part of the system, this article in the same magazine talks a bit more, goes into more detail about using the base station, configuring decoders. This talks a bit about the speed mapping, the fact that you basically, when you send a command to set the speed, it's not just a literal, if you say 50%, it won't just drive the motor at 50%, because there are things like friction in the motor and in the wheels, such that the speed has to be above 0 before it will even start moving. So you can basically compensate for the characteristics, so that you get a smooth progression of speed as you accelerate. And we talk a bit more here about those function outputs, the 4 outputs you can use for lights and sounds and so on. So that's just a general overview of DCC. So having described the decoder in December and the base station in January, then in February we published the remote controller. Now this plugs into that socket I mentioned on the base station. In fact, you can daisy chain multiple controllers. So you can see here you have a small screen, you have a speed control and some buttons. So even if you're just one person, you might want to have this remote controller because it makes it more convenient to control the trains while you're doing other things on the base station. But if you want to control trains with your friends or family members, you could have 2 or 3 of these, chain them as shown here, and they can all be used simultaneously. I think there's a maximum of about 4. Um, it may be possible to have more. It just depends. Basically, if there are too many of them, then the messages will be too frequent and it might bog down. So it's a very simple circuit. Microcontroller here, 6 buttons, screen, bicolor LED, potentiometer with the rotary knob, and then the rest is just circuitry for programming the chip and for connecting to the base station. You can see the board here is pretty straightforward. That blue thing is the screen module. It's an organic LED. 6 push buttons, 1 rotary potentiometer with a knob, the 2 sockets for input and output, microcontroller, and that's pretty much it. And cleverly, all the components mount on the back of this panel, which becomes the lid and already has the labeling. So you don't have to do the labeling, you don't have to cut the lid, you just assemble the PCB, put it in the box, and you're basically finished. There's a little bit of hole cutting, as you can see here, to make the 2 cutouts in the box, but that's pretty much it. And we talk a bit about how to use this. Parts list, and some information on the term. You can connect the base station to a computer and monitor what it's doing. And you can see you can see here the latency. In other words, the delay between you adjusting the remote controller and it sending the message to the train. So that's the remote controller. That's the third part of the system.